Good afternoon, everyone. This is Mr. Couple. In this video, I'll be teaching you about nuclear decay and radioactivity. I have three main ideas that I want you to learn from this video. The first is that nuclear decay is the process by which an unstable atomic nucleus loses energy by radiation. We kind of talked about that last time. I showed a video of that sample of radioactive lead that was spewing out those particles. And so realize that when a nucleus is unstable, it will fall apart and it will end up releasing these particles and they'll carry energy away from the nucleus. The second idea is that there are the two most common types of nuclear decay, or the two most common types of radioactive decay. There's two words, nuclear or radioactive decay, are alpha decay and beta decay. And that's the main focus of what I'll be teaching you guys about today is alpha and beta decay. And then lastly, I want to talk to you about radioactive half-life, which is defined as the time it takes for half of a large sample of that material to decay. Before we go any further, I want to review what we learned about last class. So this is a really important word that you need to know. It's the word nucleon. And nucleon is defined as a particle that's found inside the nucleus. So there are two particles that count as nucleons, the proton and the neutron. And so remember that the proton, it has a charge, which means that it feels the electric force, the electromagnetic force of charged objects exerting a force on each other, and it also feels the nuclear force, the strong nuclear force. So the proton feels the electromagnetic force and the nuclear force. The neutron, though, doesn't have a charge, so it only feels the strong nuclear force. So let's remind ourselves that what happens is in this picture here, you can see that all these arrows, they're showing that this neutron and this proton, they're attracted. This proton and this neutron, they're attracted. And so every nucleon is attracted to every other nucleon as long as they're close together. Because remember, the strong nuclear force has its biggest weakness is that it has a very short range. So as long as the nucleons are close together, they will all attract each other. And it creates this sort of like a binding where all the nucleons are stuck together and trapped to each other. Because remember, what's happening is that protons, so if this is I'll do it with green. If this is a positive charged proton and this is a positively charged proton, what will happen is they'll actually try to repel each other and they'll try to disassociate or rip apart the nucleus. And it's the strong force that's holding it all together. So remember that there's a battle inside every nucleus between the electromagnetic force, which is trying to pull apart, repel apart the protons, and then the strong nuclear force, which is trying to hold everything together. Let's look at this chart. So this chart is showing you, this is a chart of every observed nuclide. So the idea is like, imagine a number of neutrons on the vertical axis, and then imagine a number of protons. Like just pick any two numbers. Pick a number of neutrons, pick a number of protons. And in this chart will show you whether that nucleus has been observed and whether it's stable or whether it will decay, whether it's unstable and it will fall apart. So if it shows up as a black box, then that means that it's stable. So you can see there's very few here that are actually stable. Most nuclides that you can form out of protons and neutrons, most of them are unstable. So that's our first observation, is that most configurations of nucleons are unstable. Now, if you look down at the small nuclides, which are down here, you'll notice that they tend to have, the stable ones, tend to have the same number of protons, Z, and the same number of neutrons, N. And so you'll notice that the stable ones in here, they all fall along this same line right there, which is the line of protons equals to neutrons. If we look at the middle-sized nuclides, so those are the ones in this region here, you'll notice that they always fall above that line of Z equals to N. So this line is Z equals to N, proton number equals neutron number. And in the middle-sized nuclides, they all fall above that line, which means that they have extra neutrons. So middle-sized nuclides have extra neutrons. And the reason why is because of the weakness of the strong force is its short range. So when the nucleus starts to get too big, you start to have to add on extra neutrons to hold everything together. And then lastly, if you look at this very furthest out range, there are no stable nuclides that are greater than lead. And so this very last box here, I'll zoom in on it. This very last box right here, this one, right there, that's lead 208, PB 208. And that's the largest nuclide that has been observed to be stable. That every other nuclide past that point, every single one of them is unstable. Now let's look at these colors. So these colors tell you what type of radioactive decay is going to occur. So the orange and the blue colors, those are called beta decays. There's two types of beta decays. There's a positive and a negative. We'll talk about both. The yellow are called alpha decays. Green is spontaneous fission, which means the nucleus just falls apart. Then there's some proton emission, there's neutron emission, and then there's stable and then unknown. The only ones that I'm going to be focusing on with you guys is I'm going to be talking to you about beta and alpha. That's my plan for today. Beta and alpha. That's my plan to talk about today. We don't really want to go into details about that other stuff. You can take IB physics if you want to learn that stuff. All right, I have three questions here that are going to be in the lesson for today, and I'm just going to briefly talk about them now to help you answer them on the lesson. Question one: when does alpha decay occur? So what you'll notice is there's the alpha decay. So the alpha decays primarily happen out in this region up here, and that's when the nucleus is too big. So alpha decay primarily occurs for large nuclides, when you have a nucleus that's really, really big. And the reason why is because the bigger the nucleus gets, the less the strong force is able to exert its influence on the nucleus because of its short range. And eventually the electromagnetic force ends up winning and just rips apart every large nucleus eventually. Question two: when does beta plus decay occur? So if we look at beta plus, that's the orange ones. So beta plus is here. So beta plus it seems like it's always occurring beneath this line of stability. So this region of stability here, the beta plus is occurring beneath it, and then the beta minus is occurring above it. And so what we say from that is that beta plus occurs under two conditions. Well, let's just say one condition. Beta plus occurs when you have too few neutrons. So too few neutrons. And then beta minus occurs when you have too many. If you have too many neutrons, you'll beta minus decay. And if you don't have enough neutrons, you'll beta plus decay. So beta minus, too few neutrons, beta plus, sorry, I said that backwards. Beta minus is too many neutrons, right? We're too high. We're too high up on this neutron. The number of neutrons is here. We're too high up on that neutron graph. And then if you're below the line, you're too low, which means you don't have enough neutrons. You have too few. Let's look at alpha decay in more detail. So what is alpha decay? Alpha decay happens when the nucleus spits out an alpha particle. An alpha particle is two protons and two neutrons. So you can see in this picture, there's two protons, and then you got your two neutrons here. That's a neutron and that's a neutron. This is a picture of alpha decay happening for uranium ore. So there's a rock that's uranium. Uranium is used to make nuclear bombs. We'll talk about that next week. But you can see these trails that the particles of radiation are leaving behind as they shoot out from the uranium material. So let's look at this in a little more detail. So there are three things you need to know about nuclear decay. The first up is this starting off is called the parent nucleus. So the starting nucleus, which is a large unstable nucleus, it's the parent. Then what will happen is it will pop and it'll spit out the alpha particle. The alpha particle, that's called the radiation. So that's the particle that's going to get shot out. And then what's left over is a modified, smaller, more stable nucleus. And we call that nucleus the daughter nucleus. So the parent nucleus is what you start with. It's unstable. It falls apart. It spits out this alpha particle. And then what's left over is called the daughter. And the daughter is more stable typically than the parent nucleus is. Because this is happening because the nucleus is trying to become more stable. What we want to do now is we want to try to construct what we call a decay equation for these alpha decays shown in this picture here. So let's figure out what element this is. So it has 92 protons. So if I go pull up my table of elements that I have, I attach this to the assignment from last class. Let's see if it's still in here. Week 5, where is it? Oh, it's not here. Oh, there it is, table of elements. Okay, cool. I'm gonna pull that up. So we want to go look up element number 92 because it has 92 protons. Remember, that's the number that determines the name of the element. So let's go look up what element this is. So number 92 on our chart is right there. So number 92 is uranium. So I'm going to write down the symbol for this element. So I've got uranium and it's number 92. Now I have to figure out what number to put on top. Well, there's 92 protons and 146 neutrons. The number on top is the total number of nucleons, which means I have to add these together. So 6 plus 2 is 8. 9 plus 4 is 13. Carry the 1. That's 238. So this is uranium-238. Now, what's going to happen to uranium-238? Well, it's going to turn into something I don't know what it is. But I do know this. I know that it's going to also lose 4 nucleons, 1, 2, 3, 4, 2 protons, which is, if you go look up 2 protons, is helium. And so that's what happens in alpha decay is this alpha particle gets spit out. So it actually turns out that that alpha particle is really just a helium nucleus. So now let's figure out how many protons there are, how many neutrons there are, and let's figure out what this daughter nucleus is. So we know that the 92 protons has turned into, well, we've lost 2, so that means there's only 90 protons now. And if we go look up what element has 90 protons, that's thorium. So let's go find that just to show you. So uranium is down here, 90, 92. And so we're over here at number 90, that's thorium. So the daughter nucleus is thorium, and then we can figure out how many nucleons are by, well, I mean, we can figure out that, well, yeah, because it also lost 2 neutrons, so there's 144 neutrons. We could add these up, or you could think, hey, I lost 4 nucleons, and 234 losing 4 gives me 238 losing 4 gives me 234 for that thorium. So this is called a decay equation, and it shows us the alpha decay of uranium-238 when it turns into thorium-234, and then it shoots out this helium particle, gets shot out of the nucleus. Let's do another one. So here we've got 88 and 124. So remember I have to add these up. So 7 plus 8, that's 15. Carry the 1. And then I'm going to have 11, carry the 1. And then that's going to be, what did I do wrong? I don't even know how to do math, guys. 8 plus 2 is 10 plus, wait, what am I doing here? I have to do 8 plus 2 is 10, 11, carry the 1, 215. Okay, so that's 215. There's 88 protons, and so I got to figure out what this guy is. So what's 215 with 88? So number 88 is radium, so I put Ra. So what's radium going to do? Well, radium is going to lose 2 protons and 2 neutrons, meaning this 214 is going to go to 211. 2 protons off this is going to be 86. And if we go look up what that turns into is if we lose 2 protons, so there's losing, whoops. So here's losing, come on, here's losing 1 proton, here's losing another proton. So it turns into radon. So that's Rn. And then we're going to spit out the 4,2 helium. So this is the format that you'll always find with alpha decays is that you have to take whatever the parent was and just lose 4 nucleons and 2 protons, and then you'll have the daughter. What 2 mathematical equations are represented in this decay equation? So you'll notice that what happens is you actually have 2 equations here, and they're conservation equations. So I'll write them down. So we have 238 is equal to 234 plus 4. And the second equation we have is on the bottom, 92 equals to 90 plus 2. And the way we write it this way, the reason why physicists write it this way is because each of these equations is actually a conservation equation. So this bottom equation here, this is the conservation of charge. Conservation of charge. Net charge can't be created or destroyed. The top equation is the conservation of mass. Well, it's actually the conservation of the baryon number, but I'm not going to talk to you guys about quantum numbers. So we'll just call this the conservation of mass. Mass can't be created or destroyed. Construct the generalized alpha decay equation. All right, so when we say generalized, it means, you know what? These were specific equations. Like this is specific to uranium-238. This is specific to radon-215. But what would a generalized equation look like? Well, generalized equation would have some element X with A nucleons and Z protons. And what would happen is it would turn into a daughter, which we'll call Y. It'll turn into a daughter Y plus 42He. Always have the 42He, the alpha particle radiation. But the daughter is always going to have 4 fewer nucleons and 2 fewer protons. And so this is the generalized equation of what all alpha decay always looks like. And so you'll notice that all you have to do is if you want to find this number here, you just have to subtract 4 off that number. And if you want to find the number on the bottom, you just subtract 2 off of that number. And that's what we call a generalized decay equation. Let's look at beta decay. So alpha decay happened when the nucleus was really big. When does beta decay happen? So beta decay happens in these regions here. So we talked about it when there's either too many neutrons or too few neutrons. So let's go into a little bit more detail and try to understand what's going on there. All right, so how could a nuclide in the blue region become stable? So if I was a nuclide up here, let's say I'm that one and I'm unstable. So if I'm this nuclide here and I want to become stable, what do? Well, there's two things you can do, right? I could go this direction by gaining protons, and that would allow me to become stable. If I just added a few more protons on there, I could become stable. Or I could drop down to here by losing some of those extra neutrons. Well, the best of both worlds is to do both. And if we do both and go this way, we'll actually be losing neutrons and gaining protons, where there's a really easy way to do that. You could take the extra neutrons that we had and just turn them into a proton. And so that's what happens is that beta, this is beta minus. So beta minus decay is when a neutron turns into a proton. And then the opposite is true for the other direction. So if you have two, where is it? On down here. So if I was a particle, let's do it up. Yeah, that's fine. So we'll put it right here. So we'll say if you're this guy right there, what could you do to become stable? So you could either lose some protons or gain some neutrons. Well, the easiest way to gain a neutron is to take a proton and turn it into a neutron. The nucleus already has those protons in it, so why don't we just switch sides and swap them over to the neutron side? And that's exactly what happens inside the nucleus, is that a proton will turn into a neutron. And then this is called beta, this is beta plus decay. So beta plus decay is when a proton turns into a neutron. Okay, let's see how this actually plays out. So here's a nucleus that's going to have a proton. It has too many protons, and then one of those protons is going to turn into a neutron. So let's go ahead and fill out this equation. So first up, I got to count how many nucleons there are. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So I've got 19 nucleons. And there are, let's count the protons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 protons. Okay, now we're just got to look up to see what element this is. So if I have, I think I said 10 protons. So 10 protons is over here, it's neon. So this is neon, neon 19. Now what's going to happen? So what we realize is that this right here, this proton, that proton is going to, what did I click on? That proton is going to turn into this neutron. So what will happen is we are going to lose a proton, but gain a neutron. So there won't be 10 protons anymore. There's only going to be 9 because we've lost a proton. But if you still count the number of nucleons, when a proton turns into a neutron, it's still a nucleon. So the number of nucleons is not going to change, but it's no longer going to be neon. It will have transmuted into fluorine. But then if you look at this, this doesn't work because charge isn't conserved, because this number 10 has to be equal to this number 9, and it's not. So that means we have to add something on here to make them equal each other, and I have to add a 1 here. And you think to yourself, all right, what particle has 1? We might think it's a proton. If I put a 1 here and I put a 1 here, that would be a proton. But then you realize, wait, that doesn't work, because then there would be 20 up here. So what is this thing? And so it actually turns out, surprisingly, that it's actually an electron with a positive charge on it. And we actually call this a positron. And this is actually a thing. There are positively charged electrons. They're called positrons. They are antimatter. So when a proton turns into a neutron, it has to spit out antimatter, which is pretty cool. And then it turns out that if you actually check to see if momentum is conserved in this, it turns out that it's not. And you have to actually add one other particle in there, and it's called a neutrino. And I'm just going to put it there for completeness. I don't expect you guys to know what a neutrino is. They are very tiny. Neutrino comes from Italian for the little one. It was this almost like a ghost particle, like this tiny little particle. And we just had to add it in there so that way momentum would be conserved in this process. Okay, let's look at how you turn a neutron into a proton. So we'll do a similar procedure. So once again, I'll count up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Oh, it's 19 again? All right, that's fine. And now I'm going to count up the protons. There's 1, 2, 3, 4, 5, 6, 7, 8. 8 protons. So 8 protons, we'll go look up to see what element that is. That's oxygen. So this is oxygen 19. And oxygen 19 is radioactive. Why is this showing up? Come on, get out of there. Oxygen 19 is unstable. It's radioactive. It will decay. And when it decays, one of its neutrons, so that's this neutron right here, will turn into a proton. And when that happens, we'll end up gaining a proton, but not losing or gaining any nucleons. And if we do that, it will turn into fluorine. But now we have to make sure again that this stays balanced. So 8 and 9. So what do I have to do to 9 to make it equal to 8 is I have to subtract 1. Well, the particle with a charge of -1, that's just the regular electron. So this isn't the anti-electron. This is just a regular old electron. And it turns out that you also have to add the neutrino here, but it needs to be an anti-neutrino. So this is an anti-neutrino. So what you'll notice is when I'm putting the bars on top of it, like that little overbar there, the overbar is what you use for antimatter. So antimatter has an overbar over it. All right, so let's construct a generalized equation. So the generalized equation, so for beta plus, you're going to have the x, a, z is going to turn into a daughter y with the same number of a, but it's going to have one extra proton. So a neutron is turning into a proton up here. Or I did this backwards. I did the one we just did. It's going to have one less. So I need to do subtract 1 here. So I'll show you what I'm looking at to figure that out. So I'm looking at the 9 here, and I'm thinking about this 10. So what did I do to the 10? I subtracted 1. So that's going to be -1. I need to then add that antimatter electron, the positron, and then I need to add the neutrino. And then that's for beta plus. And so what happens is when you have beta plus decay, you get a positron coming out. That's why it's called beta plus, because it emits a positron. A positively charged particle of radiation gets ejected. For beta minus decay, so beta minus, you can imagine that a negative is going to get ejected, which is exactly what happens. So A, Z, X is going to turn into daughter with the same A, but the daughter is going to have one extra proton because we're taking a neutron and turning it into a proton, whereas over here we took a proton and turned it into a neutron. And if you want to turn a neutron into a proton, you have to spit out an electron and an anti-neutrino. And once again, because it's called beta minus decay, we can see that the minus is ejected from the nucleus. I want to briefly talk about antiparticles. So what the heck is an like when we talk about this positron being antimatter, like what the heck is antimatter? So it's a real thing. What we say is that every particle has an antiparticle. And an antiparticle is just like the original particle. It has the same mass, but it has the opposite charge. It also has the opposite of some quantum numbers, but like I said, quantum numbers is a thing we talk about in IB physics. So what happens is if you have an electron, the electron has an antiparticle called the positron. And the proton has an antiparticle called the antiproton. An antiproton has a negative charge. And the neutron has an antiparticle called the anti-neutron, but don't worry about that. So what we're really talking about here is just this existence of a positron. And something really cool happens. If an electron and a positron collide with each other, like if they meet, they annihilate each other. This is Einstein's equation equals mc squared. So if you take two particles, like one that's a regular electron, and you take an anti-electron, and you combine them and you crash them into each other, then what happens is you just get a big old explosion, and you just get pure energy coming out of there. And the energy comes out in the form of electromagnetic radiation or gamma rays. All right, let's talk some more. Okay, so now I want to talk to you guys about radioactive decay. So this process of decay, when a nucleus falls apart, it's random and spontaneous. Random meaning we can't predict it, and spontaneous means we can't affect it. It will happen regardless of there's nothing we can do to cause it to happen. So it's random and it's spontaneous. So here I have a single atom This is polonium-211. I'm going to hit play. And you'll notice that polonium-211 is unstable. Notice how it's like blah, 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 blah. And eventually, I don't know when, but eventually it's going to decay. And once it decays, it will drop down. Its mass will lower by 4 because this is an alpha decay. It'll drop down. And we're just going to time how long it takes for that to happen here. So this is in seconds. This is a computer simulation. Come on, there it goes. It finally decayed. And I'll just do that again. And I'll just keep doing this over and over again. All right, let's do it one more time. And so basically, I have no idea when this thing is going to decay because nuclear decay is random and spontaneous. I have no idea. I cannot predict when that nucleus is going to decay. It's entirely random when it's going to happen. And you might think, well, we're in trouble because, the whole goal of physics is to make predictions about the universe and figure out what's going to happen. But here's a situation where we literally cannot know when it will decay. It is impossible to know. You cannot know when it will happen. It is random and spontaneous. It just happens suddenly and it happens randomly. We have no idea when it will happen. And you might think that science is just, at this point where we can't do anything. But it turns out you can do something because if we take a large sample of polonium, then what ends up happening is it does decay predictably. If you have a large sample, now this isn't quite large enough. There's only like 100 or so here. But if you imagine you had like trillions and trillions of particles, well, it does end up decaying predictably. So let me go ahead and reset these nuclides. So what happens is you'll always notice if I pause it now, I'm at the halfway point. Look at where we are. This much time has passed. Let me do it again. I'm going to pause it when half of the particles, half of the nuclides have decayed. And so you notice that it is around that same half-life there. Like I said, we don't have enough for it to be perfect. But if you imagine you have trillions and trillions and trillions of these, every time you reach the half-life time, half of the sample will have decayed. I'll do it one more time so you guys can see it. So when I get to the halfway point there, half of the particles have decayed. So you notice that half of these poloniums have turned into lead, and the other half remain as polonium. So this concept is called the half-life time. So what we realize is that the decay happens randomly and it cannot be predicted. However, a large sample does decay predictably. So look at this. This is a graph that was taken from an experiment where we had radioactive magnesium-28, and we allowed it to decay. And we just measured the amount that remained after certain amounts of time has passed. So the question is, what is the half-life of magnesium-28 from this graph? This is experimentally determined. We measured how much magnesium was left after certain intervals of time. Well, the half-life, it's the time for half to decay. So after a half-life has passed, we would expect for the amount to remain to be half. We expect half of it to remain. And so if we go over from there to right there, we notice that that means the half-life is 20 hours. So the half-life time, we write that as T subscript 1/2. The half-life time is 4 hours. And you can see what happens if we wait another 4 hours. Sorry, I don't know why I said 4. How many times did I say 4? 40 hours. If we waited another 4, what am I doing? It's not even 40. It's 20. It's 20. I'm losing my mind, guys. This is what happens when I'm here talking to myself. If we waited another 20 hours so that we were at 40, then how much would remain? So that's to here. And you'll notice that if we go over from there, it's half of a half. So that's 25% remain. So after one half-life passes, 50% remain. Another half-life, you have 25%. If we go out to another half-life, it'll be 12.5%. And you can see that it's slowly decaying down to 0, but it never actually quite reaches 0. It will asymptotically approach 0, but it'll never quite make it there. This is only if you have like a super, super large sample. If you had a small sample, it would make it there for sure, eventually. So the half-life is defined as the time it takes for half of a sample to decay. So here's a better visual of what's going on here, as we saw in that other graph, is that after one half-life passes, half of the sample remains. After two half-lives pass, 25% remains. After three half-lives, about 13% remain, and so on. And so you can see that it's just random, like there's no pattern here of which ones are decaying, they're just randomly happening. So the parent nuclides are those dark ones and the daughters are the light ones, and you can see that as time passes, fewer and fewer and fewer remain. A lot of people think that if you start with 100 and a half-life passes, you'll have 50, and if another half-life passes, you'll have 0. Because like, well, if 50 decayed in the first one, then 50 would decay in the second one. That's not how it works. Every time a half-life passes, half of them decay. Search for a mathematical pattern in the rate of decay. All right, I'm going to end with this. If you want to stay on, if you want to stay tuned, I will actually solve a practice question, which is very similar to the one on the worksheet that I gave you. But I want to finish this up here. I believe I'm at my 30-minute mark here. I want to find a mathematical pattern. So what we're noticing is when the number of half-lives, so I'll call that n, this is going to be the number of half-lives. So when there's 0 half-lives, the amount that remain, so let me do it like this. I'll do like number of half-lives, and then I'll put n for like the number that remain. So when there's 0, there's 100% that remains. After 1 half-life, there's 25%. After 2 half-lives, there's 12.5%. But you know what I'll do is instead of writing these as not decimals, what are these called? Percentages, I'll write them as fractions. So here we have 1 out of 1. Here, after 1 half-life passes, you have half. After 2 half-life passes, you have a fourth. After 3 half-life passes, you have an eighth. After 4 half-lives pass, you have a 16th. And so what we want to do is we want to find a pattern that relates these two to each other. We want to find a pattern. And so it turns out that what the pattern is you take the number of half-lives and you make that the exponent of the number 2. So if n is the number of half-lives, you can see that when there's 1 half-life, not 2, it's 1 half, sorry guys. You take the number 1 half, 1 over, let's do it as 1 over 2 to the nth power. That'll make more sense. 1 over 2 to the nth power. So here we can see that this would be 1 over 2 to the first power, 1 over 2 to the second power, 1 over 2 to the third power, 1 over 2 to the fourth power. And so that's the mathematical relationship. It's that the number that remain is going to be equal to 1 over 2 to the number of half-lives that have passed. I'm using capital N for the number that remain and lowercase n for the number of half-lives that remain or that have passed. All right, that's it. So if you guys want to tune out now, go ahead. I'm going to go ahead and solve this problem, which is very similar to the problem that I left for you on the assignment. So if you go do the assignment and you have trouble, come watch the end of this video. This question is about radioactive half-life and nuclear decay. A sample of Neptunium-240 is placed in a sealed container and left to decay. So it's sealed, that way we don't have any of the material escaping. So we know that if the Neptunium is no longer detected, that means it's still in the container, it's just turned into a different element. It's transmuted into something else. The mass of the sample measured every 20 minutes is shown in the table below. Okay, so 20 minutes pass, we have 63.5 grams starting at 80. Start at 80, we have 63.5, then we measure it again, we have 50.4, we measure again, and we have 40. It says determine the half-life of Neptunium-240. So starting from 80 grams, if a half-life passes, then how much should we have left? We should have 40 grams left, because half of it will decay. So at what time did we have 40 grams left? It was 60 minutes. So the half-life time is 60 minutes. After an unknown amount of time, the sample is found to contain 10 grams of Neptunium-240. Determine a number of half-lives of Neptunium-240 that have passed since the sample was first placed in the container. All right, so if we were first placed at 80 and then we let a half-life pass, that would take us to 40. If another half-life passed, that would take us down to 20. And if another half-life passed, that would take us to 10. Okay, there we go. We're at 10, which is where it said we should be. And now you just have to say how many half-lives was this? Well, each time there was an arrow that represented a half-life. So there's 1 half-life, there's 2 half-lives, and there's 3 half-lives. So that means that the time has been equal to 3 half-lives. So 3 half-lives have passed. How much total time has passed since the sample was first placed in the container? Well, if 1 half-life is 60 minutes, and that means 3 of those have passed. So I can solve this by saying that if the time is equal to 3 half-lives, and the half-life time is 60 minutes, then we can see that 180 minutes have passed. All right, have a great day, everybody. Thanks for watching the video, and I'll see you next week.